Okay, so section 6.4 is area and how it relates to the definite integral. So we've already talked about the definite integral representing the area under a positive function. So if you have a function from a to b that is completely above the x-axis. So all of the y values are positive on that interval from a to b. Then when you integrate, and this will be the function f, when you integrate from a to b, f of x with respect to x, that ends up representing this area. But now we're asking, what if we want to find the area bounded by the curve in the x-axis where the curve dips below the x-axis? So something like this. Where, I don't know, let's say this is A, and then this is B. So we would want to know this area plus this area. So when we evaluate a function, a continuous function on the interval from a to b, the definite integral is either going to represent scenario 1, so the total area bounded by the curve in the x-axis from a to b, if f is non-negative. So that was that first picture. If the function is positive on the interval from a to b, the integral from a to b is going to represent the area under the curve and above the x-axis. However, if the difference between, if the function does dip below the x-axis on the interval from a to b, like this graph, let me change this actually. Oops. And I'm actually going to call this A over here. So let's say we wanted this area plus this area. Okay. So if we were to integrate this function from a to b, the integral would actually end up being the difference between the area above the x-axis and the area below the x-axis. And that's because if you, let's call this x value c. If we were to integrate from a to b, a to c, this function, we would end up with this area. I'm going to call it area 1. If we were to integrate the function f from c to b, we would end up with a negative value, because the function is dipping below the x-axis. So I can call this area 2, but it would actually be like the negative area. So if we were to integrate from a to b, it would actually be area 1 minus area 2. So if the area below the x-axis is smaller than the area above the x-axis, then we would still end up with a positive value for the definite integral. But if the area below the x-axis was greater than the area above the x-axis, then we would end up with a negative value for the definite integral. We, however, that's not what our goal is in this section. So our goal in this section is going to be to find the total area bounded between the function and the x-axis. So to find the total area for this particular function, the total area would be area 1 plus area 2. In area 1, we already can see how we would find area 1. Would just be integrating from a to c, so over the interval for which the function is positive. And we could end up with area 2 if we were to just multiply the definite integral from c to b by a -1. So then that definite integral, which was a negative value, multiplied by a -1 would end up being a positive area. So then if we replace area 1 with the integral from a to c of the function and do plus and replace the second area with -1 times the integral from c to b of the function with respect to x, that would actually give us the total area in blue. So we're going to look at some actual examples now. So if we want to find the total area bounded by the x-axis in the line y equals to -x plus 1 on the interval from 0 to 2, let's first sketch what that looks like. So I have my x and my y-axis. Okay, so this is the line that has a y-intercept of 1 and then a slope of -1, so I'll go down 1, right 1 to find the next point, down 1, right 1. And the line is only defined from 0 to 2. So we want to find the area between the curve and the x-axis. So the first section would be here. And then to +2. So we want to find between the curve and the x-axis here. So because the function dips below the x-axis on this interval, I'm going to have to split up the area. So this is area 1 and this is area 2. So the total area will be area 1 plus area 2. And to find area 1, I'm going to integrate from 0 to 1 the function -x plus 1. So I can just evaluate the definite integral here since the function is going to be positive on the interval from 0 to 1. So we'll have -1/2 x squared plus x. And then by fundamental theorem of calculus, that'll be -1/2 times 1 squared plus 1 and minus 0. So simplifying that, we get 1/2. Now the second area, because it's below the x-axis, I'm going to have to multiply by -1 and integrate from 1 to 2 that same function. So we have the -1 hanging out up front. The antiderivative of -x plus 1 we already know from above. And then applying fundamental theorem of calculus. Oops. Should use parentheses here actually. And when we simplify, we end up with 1/2 again. So the total area ends up being 1/2 plus 1/2, which is just 1. Now the areas of each of kind of the triangles that are created by the x-axis and the line have equal areas. So that means there's an equal area above the x-axis and below the x-axis. So if we were to actually integrate from 0 to 2 this function, we would end up with 0 because the areas would end up canceling out. The area above the x-axis minus the area below the x-axis is just 0. So the total area bounded between the x-axis and the function is 1. Okay, so now we want to find the total area bounded by the x-axis in the curve y equals to x cubed. So sketching what that looks like. Okay, so from -2 to 2. Okay, we know x cubed passes through the origin, then -1, -1, 1, 1. And then it goes down to -8 when x is -2 and +8 when x is equal to +2. So it looks something like that. The interval from -2 to 2. So I'm going to highlight our total, like the area that we're trying to find. This is another one where it looks like the area above the x-axis is equal to the area below the x-axis. So if we were to integrate this function from -2 to 2, we would just get 0. So we're going to have to break it up. So I'm going to call this area 1 and this area 2. So again, the total area will be the sum of those two areas. So the first area is below the x-axis, so I'm going to need to multiply the integral by a -1 and integrate from -2 to 0. So then fundamental theorem of calculus, that'll be 1/4 times 0 to the 4th minus 1/4 times -2 to the 4th. -2 to the 4th is 16 divided by -4 would be a -4. So that's -1 times -4, which is just 4. Probably just go directly to saying 4. And then the second area, which is above the x-axis, will integrate from 0 to 2. So fundamental theorem of calculus. We end up with 4. So the total area here bounded by the curve and the x-axis is going to be 4 plus 4, which is 8. Okay, and for a piecewise function, let's go ahead and sketch the graph. Now, you can also use your calculator to look at what the graph is going to look like, or to find where x-intercepts are, because remember x-intercepts is where the function would end up changing sign, so where it would dip below the x-axis or switch to go back above the x-axis. So you can always use your calculator too, but these are pretty basic functions that we can just sketch by hand easily. Okay, so x squared graphed from -2 to 1 of the point -2, 4, -1, 1, 0, 0, and 1, 1. I'm going to switch colors, even though it's the same function, but just to represent how I'm going to have to split up the areas, I can graph the line 2x minus 1. So that has a y-intercept of -1, a slope of 2, so I would go right 1 up 2. It would put me at 0, or sorry, at 1, 1, even though 2x minus 1 is not defined for x equals to 1. When x is equal to 1, we use x squared. But if we substitute the endpoints of this interval in for x, that'll kind of give us an idea of where the function starts and ends. So if we substitute 2 in for x, that would give us 3. And we know that's a line. So it looks something like that. So since we want to find the area bounded by the curve and the x-axis between -2 and 2, but this is a piecewise function, I'm going to have to, even though the curve is completely above the x-axis, or it intersects the x-axis as well, I'm still going to have to break up the area because I have to use the different pieces of the function to integrate. So I'm going to have to first find the purple area by integrating from -2 to 1. Now if the function dipped below the x-axis, I would have to split up the areas more, split up the integrals more, but because there's just an x-intercept, that's okay. So this is area 1, this is still part of area 1. And then the second area will be between the line and the x-axis here in blue. Okay, so to find the first area, that'll be the integral from -2 to 1 of x squared. So it's 1/3 x cubed from -2 to 1. So that ends up being 1/3 plus 8/3, which is 9/3 or 3. Oops. And the second area, I will integrate from 1 to 2, 2x minus 1. So that's x squared minus x. So that just ends up giving me 2. So the total area is equal to 3 plus 2, which is 5. So on your homework, you can sketch the graphs, or you can use your calculator to look at what the graphs look like, or determine if there's any x-intercepts and if the function dips below the x-axis at all.